Understood. Here is your rewritten script. Same structure and flow, fully paraphrased, delivered as one paragraph, and fully YouTube policy safe. Right now, inside a laboratory in the United States, there's a number that shouldn't be there. Not because it's incorrect, but because it's correct, and no principle of classical physics can account for its existence. A machine carried out a computation as though it occupied multiple versions of reality simultaneously, not as a metaphor, but as something measurable. The scientists behind the experiment verified it, reconstructed it, and repeated it, expecting to uncover an error. There was none. To grasp why this one result unsettled people who rarely get unsettled by numbers, you have to travel back over 4 decades to a moment nearly everyone overlooked. A physicist stood before an audience and made a statement that, at the time, sounded like science fiction disguised as humor. If you truly want to simulate nature, he argued, you'll need a computer built the way nature itself is built. Not simply a quicker version of existing machines, but an entirely new kind of device. In that era, the notion seemed nearly ridiculous. Computers were massive, sluggish by modern measures, and their inner workings were fully understood. Everything ultimately came down to a switch flipped on or off, a 1 or a 0, the bedrock of every bank, every phone, every program ever created. But nature never signed up for that arrangement. At the atomic scale, a particle can hold several possible states before any measurement occurs, acting as both a wave and a point simultaneously, while 2 particles can remain linked across enormous distances, as though the gap between them ceases to matter. The physicists recognized what everyone else was missing. If the universe operates on quantum principles, why attempt to capture it with a machine that doesn't? It's like trying to portray the entire ocean using a single droplet. From that insight came the concept of a new kind of bit, not a switch, but something resembling a coin still tumbling through the air, holding both heads and tails at once while it spins. Now, picture hundreds of these spinning coins connected together, where each additional one doesn't merely add capacity, but multiplies the total possible states until the number of outcomes grows too vast to even record. That's the potential. But here's the catch. Such a system is extraordinarily delicate. A tiny vibration, a sliver of temperature change, a pulse of electromagnetic interference. Any of these can destroy the entire computation in under a second. For decades, most physicists believe a machine capable of preserving this fragile state long enough to be practical was realistically unachievable. Yet researchers pressed on, developing novel materials, chilling processes below the temperature of deep space, shielding against every conceivable disturbance. And then, during one round of computations, something occurred that caught everyone off guard. The machine produced an answer that classical logic couldn't account for. Some assumed a malfunction. Others blamed faulty code. They verified it repeatedly, and the result stood firm. For the first time, a concept confined to theory for 40 years was displayed on a screen before them. Undeniable. And that sparked a question far more disturbing than the result itself. If a machine can accomplish this now, what happens as it improves? What did it just expose about computation, or about reality, that made seasoned physicists begin discussing a rewrite of the rules? Envision the room where this unfolded. Quiet, undramatic, chilled to the point where familiar laws of daily experience begin to dissolve. No vibrations, no electrical buzz. And at its heart, an apparatus resembling a chandelier more than a computer. What astonished the team wasn't merely the velocity. It was the manner in which the machine reached its conclusion. A classical computer examines one option, then another, then another. Even Earth's swiftest supercomputers, at their core, process sequentially. This machine acted as though it were surveying an immense range of possibilities all at once. And in certain experiments, the correct answer seemed to surface before the search should have concluded. To human reasoning, that resembles a breach of common sense. To quantum physics, it's simply routine. The physicists who launched this entire field once remarked that anyone who believes they understand quantum mechanics doesn't actually understand it. And that observation has never rung truer than today, as these experiments leave even veteran physicists feeling like beginners again. The most bizarre element is superposition itself. Until measured, a quantum bit refuses to settle on a state, existing instead as a collection of simultaneous probabilities. That notion proved so unsettling that one of history's most celebrated physicists devoted years to demonstrating the theory must be flawed. He simply couldn't accept nature operating this way. Yet experiment after experiment contradicted him, proving the universe has no obligation to make its rules feel sensible to us. Then something even more peculiar emerged. As scientists incorporated more of these delicate quantum bits, the system's behavior didn't merely expand. Beyond a certain threshold, it grew so intricate that forecasting became nearly hopeless, feeling less like a machine executing a job and more like something engaging directly with the mathematical framework beneath reality itself, not conscious, not sentient, but accessing a feature of nature forever beyond a classical machine's reach. Here enters quantum mechanics' most bewildering discovery, entanglement. Two particles born together, then split apart, one carried across a room or across the solar system, and intuition insists their bond should vanish, yet experiments declare otherwise. Measuring one instantly fixes the state of the other. One physicist famously derided it as spooky action at a distance, intending the phrase as criticism, but the theory prevailed regardless. Today, that eerie phenomenon forms the very foundation of how these machines compute. The quantum bits don't operate independently, but merge into a single interconnected system where altering one immediately influences the rest. Something classical machines have no counterpart for, and precisely why problems once labeled unsolvable are beginning to crack. But the further the research advanced, the odder the questions became. Why does nature permit such states to exist at all, and why would a universe embed such immense computational depth into the basic fabric of space? Some physicists ventured something even more daring. What if the universe itself is a quantum system? What if every particle, every star, every galaxy participates in a computation running for nearly 14 billion years? The field's founder never asserted this outright, but the doorway he opened has drawn an entire generation of physicists toward a radically different vision of reality. Perhaps a quantum computer isn't a human invention at all. Perhaps it's our first attempt at speaking a language the universe has employed since its very beginning. And if that holds true, the next breakthrough might transform not just technology, but our very conception of what reality is. While the public fixated on processing speed, something subtler was unfolding behind closed doors. Certain findings were so strange that researchers withheld them for weeks before publication, inspecting every cable, rewriting every line of code, swapping hardware, repeating everything, and the answer never wavered, which pointed to only one conclusion. The flaw wasn't in the machine. The flaw might lie in our understanding of reality itself. Imagine a maze containing more pathways than anyone could tally. A classical machine navigates it turn by turn, and no matter its speed, it must still search. While a quantum machine behaves as if it perceives a whole maze simultaneously, not by violating physics, but by exploiting laws our minds were never designed to visualize. Physicists label this interference. Every probability amplifying the correct route, while erasing the wrong ones until, almost like a conjurer's trick, a single answer remains. Then arrives something harder still to explain. In certain experiments, quantum states endured longer than existing models said they should, as though the system had discovered a way to shield its own fragile information. Something that shouldn't happen given how vulnerable these states are to the faintest disruption. Some attributed it to superior materials, others to refined error correction, but a handful pose a far bolder question. What if we don't truly comprehend how nature stores information in the first place? That inquiry extends beyond computers to the cosmos itself. Physicists have long recognized something odd about information. It almost never genuinely vanishes. It can transform, disperse, become inaccessible, yet nature's deepest laws appear to prohibit its total annihilation. This is precisely why black holes have fueled decades of fierce dispute. If even a black hole cannot fully erase information, where does it end up? That puzzle remains among physics' greatest unsolved questions, and unexpectedly, quantum computing research has begun supplying fresh hints. Certain mathematical models have exposed a striking parallel between how quantum errors are corrected and the theories describing spacetime's architecture. This doesn't mean anyone has decoded the universe, but the similarity was compelling enough that top physicists are now watching intently. The objective was never wealth or faster internet. The objective was learning the language nature speaks, because conventional computers merely imitate physical processes, while these machines strive to operate on the same rules governing the universe itself. And if that's genuinely the case, every quantum operation ceases to be mere calculation and becomes an experiment probing the fabric of reality. Which brings us to a question that should send a shiver through you. What if we just unlocked a door into a realm of physics where our everyday notions of time, space, and cause and effect prove to be nothing but crude approximations? What if the most astonishing discoveries still lie ahead? Because the next experiment was designed to test something many prominent physicists, until quite recently, dismissed as flatly impossible. That next experiment is why certain researchers fell silent. Not because they saw something impossible, but because for the first time, the boundary between mathematics and reality itself seemed to be dissolving. Everything in the lab appeared routine. Superconducting quantum bits cooled to near absolute zero, the system clearing dozens of inspections, every cable, sensor, and microscopic pulse tested repeatedly. There should have been no room for error. When the computation launched, thousands of signals surged through the processor simultaneously. The screen showed only numerical sequences decipherable solely by specialists, and from outside, it resembled any ordinary experiment. Then, minutes in, someone spotted something the models hadn't anticipated. The probabilities were arranging themselves as if the system already recognized which outcomes would prove worthless before the computation had finished examining them. The machine wasn't forecasting anything. It possesses no awareness, no intent. But the behavior was strange enough to provoke an uncomfortable question. Why does nature permit this at all? This is where human intuition reveals its limits. We're accustomed to a straightforward sequence. Cause first, effect after. But at the deepest levels physics has ever explored, that intuition repeatedly collapses. Students were cautioned again and again never to imagine the quantum realm the way they imagine everyday life. And that caution has never carried more weight than it does today. While headlines branded it a magic computer, the physicists inside were debating something entirely different. If a computation grows so complex that even Earth's finest classical supercomputers can't fully model it, a strange paradox arises. How do you confirm the quantum machine's answer is right? Picture a student solving problems faster than the teacher can grade them. That's roughly our current position. We've constructed a machine whose output sometimes can't be fully re-verified by the tools we already trust. And for a discipline built entirely upon verification, that's a deeply uncomfortable place to stand. The greater shock was yet to come. As researchers continued adding quantum bits, the system's complexity didn't climb steadily. It surged in a way that shattered our conventional sense of computing power. Each new quantum bit isn't merely another component. It's a whole fresh layer of complexity for the entire system, and the leap from a few dozen quantum bits to a few hundred isn't a matter of slightly more. It's a jump with virtually no precedent in the history of conventional computing. And that's when a question once dismissed as philosophy began sounding like physics. What if computation isn't a human invention at all? What if computation is a fundamental characteristic of the universe itself? Look around. Planets trace their orbits. Stars ignite and perish. Atoms interact by precise mathematical law. Light traverses billions of light years, all of it governed with mathematical exactness. But who or what is performing the calculation? Is the fabric of space-time itself perpetually computing the universe's own evolution? That idea is gathering momentum, not because anyone has proven it, but because these machines are the first instrument allowing us to glimpse just how profoundly computation may be stitched into nature. And if that's accurate, we may not merely be standing at the threshold of a new computing era. We may be standing at the threshold of understanding the actual mechanism through which reality exists at all. What awaited next was stranger still. An experiment that prompted some physicists to seriously ask, for the first time, whether such a machine could ever help reveal where time itself originates. Because at that point, this ceases to be a story about computers and becomes a story about time. Most people accept time without question. It flows forward. The past trails behind us. The future hasn't arrived. We're born, we age, and we seldom pause to wonder why time exists at all. But quantum physics poses a question capable of dismantling that entire picture. What if time isn't a foundational element of the universe, but rather the byproduct of something deeper? The physicists who began this whole journey often reminded people that nature owes us no intuition. When experiment says one thing and instinct says another, you side with the experiment. That's exactly why these machines matter so profoundly right now. They don't merely compute. They allow us to witness processes no other instrument can reveal. During some of these experiments, researchers observed something extraordinary. Once a quantum system becomes sufficiently complex, fully describing it demands an almost inconceivable quantity of information. more than even the mightiest supercomputers can contain, which raises an unsettling possibility. Perhaps the universe was never processing things step by step in the first place. Perhaps it exists all at once as one unified quantum system, where space, energy, matter, and time are interwoven far more intimately than we ever suspected. If space-time genuinely emerges from quantum connections, then these machines transcend being merely a new breed of computer. They become instruments for probing the very origin of reality itself. No one is asserting that question has been answered. Not yet, and perhaps not for a long while. But for the first time, we possess a tool that lets us pursue it experimentally rather than purely philosophically, and that, more than any single result, is what should keep you up at night.